knowledge. How much do we need? How far should we let our curiosity take us into the mysteries of science? Do we believe science will bring a better world, or is there just a desperate need to cope with problems? Is it ambition which drives us? Or are we just children, curious to play new and fascinating games? What if the game is a riddle, with the answer a riddle, a seemingly endless game in which the universe turns into layer upon layer of riddles? Still want to play? In our previous programs, we saw that light shining down from the stars through the newly invented telescope began the game of modern science in earnest. Galileo's discoveries in the heavens proved that the old ideas were wrong. The things which he saw and wrote about made it clear that nature was far more complicated than people had ever dreamed. However, light would wait another 200 years before it betrayed its link with this: magnetism and electricity. Michael Faraday, through exhaustive experiments, concluded that there must be such a thing as an electromagnetic wave, which could travel through space at amazing speed. That speed turned out to be the same speed as light. The identification last century of light as electromagnetic waves was a pinnacle of achievement. Soon, it was widely thought, science would know all there was to know. In physics, it was simply a matter of clearing up loose ends. Light was a wave in the electromagnetic structure of space. Make any kind of electrical charge, change its strength or direction, and that change flowed out into the electrical field around it. A wave of changing electric charge produced a wave of changing magnetism at right angles to it, which could produce a new wave of electric charge, a new wave of magnetism, and so on. So out went this weird disturbance, rolling on forever, unless the waves hit something which changed them, perhaps into another wavelength or into another form of energy. Here we can see the effect of strong electromagnetic waves on an ordinary fluorescent tube. The tube, hung only on a piece of string, glows with the power of the electromagnetic field. Light was seen as a similar process, the only difference being that almost everything reacted to the frequency of light, so it made the whole world visible. And it gave clues to other wavelengths, like radio.
You see, how this actually works is that when Alfred depresses the key, he creates an electrical current which moves through the batteries, down through these wires and into the main coil. This in turn creates a spark between these two conductors. Alfred, did you see that?
Down to crosscam.
Yes. Perhaps if you move a little closer. Yes.
Yes. But as swiftly as achievements came, such as Marconis Wireless, there were more questions. What, for example, was the nature of the electromagnetic structure of space? How do the waves travel? Do we live in an invisible sea of electromagnetism? It's at this point in the story of light that most people stop dead, because from here on it gets really strange. Most people cannot accept that their normal everyday experience is just one level in the layers of reality. From here on in, nothing can be directly observed. To follow the story from here requires a kind of faith, a faith in the outcome of the scientific method. A faith, ironically, first outlined by a priest 700 years ago. Remember the words of Roger Bacon? Only through careful use of the senses can we learn about nature. Logic must always bow to observation.
Do you realise what this could mean to mankind? We could transmit messages over vast distances. Who knows? We could even...
I think that deserves a toast, don't you? Thank
So,
you.
at the end of the last century, while many people thought the answers had been found, in fact, the next layer of questions were being asked. Questions about things which cannot be directly seen or touched.
I say, that's
A new chapter of experiments was about to blow away the cosy Victorian views.
Cheers, Mr. Marconi,
to
to
a
your
great future.
apparatus.
The big question for physicists 100 years ago was, how did light travel? Was it anything like sound, which also travelled invisibly? Even 100 years ago, sound had been carefully studied, and it was known that the speed of sound depended only on the medium which carried it. The whistle would change its tune as it went by. But not the speed of its sound waves. They depended on the air, and as long as the listener stood still or the wind didn't blow, the sound always arrived at the same speed. In fact, as we now know, if the whistle can go fast enough, it can break the sound barrier by catching up and going faster than its own sound. It's much the same as a boat, which can easily beat the speed of water waves, so they are left behind in its wake. The speed of these types of waves was independent of the source. Was that also the case for light? Scientists were so sure the answer was yes, that they had already invented a name for the medium in which light travelled. They called it the electromagnetic ether. Light shone from the most distant stars, so it was logical that the ether must fill all space. At this point, one of the greatest physics experiments of all time was set up to find the ether. It was based on two simple ideas. First, the Earth moves through space, so presumably it also moves through the ether. So there should be an invisible ether wind that blows by us as we roll through space. Well, that was the first idea. The second was that you could measure the speed of light with incredible accuracy if you timed it against itself. So, the Michelson-Morley experiment combined both these ideas and raced two beams of light, one against the ether wind and the other across it. The apparatus was a huge version of this model. Out goes the light beam here. Here it is split in two, one beam going out against the ether wind and one across it. Both beams then bounce back from mirrors to recombine here and come out to make this pattern. Now, if you care to work it out, the one which flows against the ether wind will definitely take longer. And knowing which beam that was, however, was unimportant, because the trick was to rotate the whole thing while watching this pattern. Thus, the winning beam should start to lose and vice versa, and the pattern should change. That would prove there was an ether wind. It never changed. In the years that followed, this experiment was done in many different ways, even on moving ships, to guarantee movement through the ether. But still, no change. Conclusion: no ether. So, light was not like sound. The whistle can catch up with its own sound depending on the train's speed through the air, but there was no detectable medium for light. The lamp cannot catch up with its own beam. Clearly there was something very odd about light waves. There sure was. Try this one. As any metal gets hotter and hotter, it starts to glow. Red at first, then more and more of the colours creep in and it gets brighter and brighter. But how bright for what temperature? Twice the temperature, twice as bright? No. A square ratio, energy of the heat to brightness? No. What then? And what about the colour? The actual answer was easy. Measure it. But explain it? Not so easy. A young German mathematician tried a different approach. He knew the problem, he knew the figures. Without worrying about any explanation, he just played around to find a formula that would produce the right figures. By 1901, Max Planck had it, a formula to predict the brightness and colour of light produced by heat. But what did it mean? What did those symbols mean? Particularly the factor he was forced to use, which he called H. It was a fixed amount, a constant. Super small though it was, it plainly suggested that light could only come out in H-sized bits or bigger. But light was a wave, wasn't it? Puzzled, Planck called his tiny H quantity a quantum of light. By itself, this proved nothing. Perhaps some odd behaviour of the electrons in the atoms as they vibrated and gave off waves was to blame. Indeed, sometimes, especially in metals, they could vibrate so powerfully they tore loose from their atoms and drifted for a time as an electric current. Thus could a powerful beam of light create photoelectricity. But something was odd about this too. Double the light and you got double the electricity. But the colour of the light had a bearing on the electricity too. The redder you went, the less energetic the electrons became until their energy, measured in volts, hit zero. And then it didn't matter how powerful the red light was, no electricity was produced. Here, yet again, was something the wave theory could not explain. But there was another very old theory that could. It went back to the ancient Greeks, the idea that light was a stream of particles, like little bullets. The particle theory explained the photoelectric problem easily. No matter how many bullets you fired, if the bullets were too weak to knock out electrons, that was that. Red bullets were obviously weak bullets. This idea, expressed by an unknown patents clerk in Switzerland, would have excited no one, except that he gave an exact formula for the energy of the bullets. He said their strength depended on Planck's H, the quantum. When the formula was tested some years later, it was found to be correct. Light was transmitted and absorbed in quantum-sized lumps, like tiny bullets, soon to be called photons. The patents clerk was Einstein. Look at this situation. What a mess! On the one hand, light is a wave. It refracts, it polarizes, it can shine through itself, all wave effects. Yet on the other hand, there's no detectable medium for the wave to be in. And now we're told it's also like tiny bullets. If a bullet is fired ahead of the train will never catch it. That's like light. But the bullet will hit the target faster, carrying the extra speed of the train. That's not like light. Light, like sound, arrives always with the same speed, even if the source moves. But to cap it off, unlike sound or bullet, the observer himself may move without affecting what he sees as the speed of light. In a nutshell, the observed facts about light defy all common sense. What would Roger Bacon have had to say about that? Well, even if you've only followed the story vaguely so far, it should be crystal clear that light was forcing a crisis. Light's one of the most fundamental things we know, and ordinary logic says it can't do the things it does. But observation says, sorry, it does it anyway. So where do you go from here? Well, I'll tell you where you go from here. Back to the drawing board, and you take a long, hard look at everything from the word go. And this time, you only accept the things you know are true. Albert Einstein tried to grasp a new reality by accepting the one fact that was common to all the observations. The speed of light is the same for all observers in all directions, regardless of their motion. Instead of trying to explain that away, Einstein used it as the basis for his special theory of relativity. And strange it is. So, here ends the story of light alone. It's been a bit like a detective mystery in which following the trail of clues has turned up something much bigger than ever expected. It's no longer just a lightly story. This will turn out to be a scientific revolution. Einstein's theory of relativity always upsets people because it seems to attack common sense. I mean, they say it even takes a physicist normally 5 years to feel comfortable with it. But this is the theory behind exploring the atom and even modern space travel. So here comes just a bit. Here comes the Einstein Express. Einstein imagined a train which could go very fast, faster even than spaceships today. What would it look like? If we obey the rules of light, then strange and upsetting results crash into our ideas. The first unusual thing we notice is that on board there isn't anything unusual at all. The guard's newspaper isn't being ripped out of his hands by the train's speed. His drink doesn't spill. Things don't fly off the table. He's probably forgotten that he's moving at all. In fact, is he moving? That depends on how you look at it. Says Einstein, that's what I'm on about. This is just one example of how things are always relative to the observer, except light, which always appears to everybody to travel at the same speed. But now let's pretend the train can go extremely fast. Let's make it go at half the speed of light, and let's make it very long. 1 light second, 300,000 kilometres. For the people on board, nothing's changed. It's just a very long, fast train. If someone in the dead centre flashed a light The driver and the guard would see it at the same time because the light would travel out equally to them. In fact, considering the length of the train, 1 light second, they would each see it at the same instant, half a second after the flash. But for someone not on board, the scene is different. From here, I can see the train is moving. I still figure the speed of light the same as they do. But to me, the light will race the speeding train, which carries the guard towards the light and the driver away. I see the flash go out, but to me, it takes only 1/3 of a second to reach the guard who is running into it, while it takes 1 whole second to reach the driver. So what I see is the guard waving first and the driver waving 2/3 of a second later. I did not see the action the same way as the people on the train. Heavy ideas. What, for example, would be the result if instead of waving, the driver and the guard dropped markers to measure the length of the train? Would I see the train the same length as them? And who would be right? Questions like these lead to amazing conclusions. Einstein proposed that time and space are one. As you increase your speed in space, it affects your speed in time compared to those you leave behind. Only tiny changes occur at normal speeds, but as you approach the speed of light, time slows until at the speed of light, there is no more time. To go faster than this, time would have to flow backwards. Einstein concluded that nothing would go faster than light. So, the Lightly story becomes a very strange story, a story which we have hardly touched, and which is well worth a closer look. Amazing beams of light. Where will they lead us next?